and then 2s2. Boron becomes 1s2, 2s2. You are done filling the 2s, then go on to the next orbital, that is the 2p. And then 2p with only one electron left, so 2p1. Is that okay? Now the next element is carbon. Carbon becomes 1s2, 2s2, and then 2p2. Don't forget that P can accommodate a max of 6 electrons, and the S can accommodate a max of 2 electrons. Is that okay? Now, element number 7, nitrogen. Nitrogen becomes 1s2, 2s2, 2p3. The next element is oxygen. Oxygen becomes 1s2, 2s2, 2p4. The next element is fluorine. Fluorine becomes 1s2, 2s2, 2p5. And then neon, atomic number 10, becomes 1s2, 2s2, 2p6. The next element is sodium. Sodium is atomic number 11. Sodium becomes 1s2, move on to the 2s2, 2p6 with 1 electron left. So move on to the next orbital, that is for the 3s1. So move on to the 3s and then indicate the last electron that is available as well. The next element, magnesium, atomic number 12, that is 1s2, 2s2, 2p6, and then 3s2. The next element is aluminium, with atomic number 13. Aluminium becomes 1s2, 2s2, 2p6, 3s2, then move on to the next orbital, that is the 3p. So 3p1. Is that okay? Now move on to the next element. Silicon, atomic number 14. One s2, 2s2, 2p6, 3s2, and then 3p2. Is that okay? Phosphorus, atomic number 15, becomes 1s2, 2s2, 2p6, 3s2, 3p3. Is that okay? Now, sulfur, atomic number 16, 1s2, 2s2, 2p6, 3s2, 3p4. So we are just following the order stated here to indicate the electrons arrangement. Is that okay? Now the next element is chlorine, atomic number 17. Chlorine is 1s2, 2s2, move on to the 3, the 2p6, move on to the 3s2, and then 3p5. The next element, argon. So argon becomes 1s2, 2s2, 2p6, 3s2, and then 3p6. That is argon. Now, the next element, potassium, atomic number 19. Potassium becomes 1s2, 2s2, 2p6, 3s2, 3p6. So right after the 3p, the next orbital is what? The 4s. So with 1 electron left, it becomes 4s1. Is that okay? Now the last of the 20, that is calcium. So calcium becomes 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So these are electron arrangements based on the Aufbaus principle. So when we are filling electrons in each of these orbitals, we start with the lowest one, and the lowest one here is the 1s, followed by the 2s, followed by the 2p, followed by the 3s, followed by the 3p, followed by the 4s, before the 3d. And please, don't forget that the s orbital can accommodate a maximum number of 2 electrons. The s accommodates 2, the p accommodates 6, the s accommodates 2, the p accommodates 6, 2, and then a maximum of 10 electrons. Is that okay? So this is the order of arrangement of electrons using the Aufbaus principle, or you can use the generalized one to guide you for atomic numbers, for high atomic numbers, elements with high atomic numbers. If you want to write a configuration, you can use this as a guide. But this one is, we are just looking at the first 20 to 30 elements arrangement. Is that okay? So that is the Aufbaus principle. So anytime I fill an orbital with electron, and let's say that let's take boron here. So in a configuration of boron, instead of me writing 1s2, 2s2, and 2p1, and then I tend to write 1s2, 2s1, and then 2p2. Once I write it this way, it means I'm violating a certain principle, and that principle is the Aufbaus principle, because the Aufbaus principle states that we have to fill orbitals of lower energy level before orbitals of higher energy level. The 2p over here has a higher energy level than the 2s orbital. So we need to fill the s orbital fully first before we move to the 2p orbital. Is that okay? So this is the correct arrangement of electrons in a boron, and not this one. Once I write it this way, I'm violating the Aufbaus principle. I'm violating the Aufbaus principle. That is the Aufbaus principle. Now let's move on to the next principle, known as the Pauli's exclusion principle. So the next one is the Pauli's exclusion principle. The next one is the Pauli exclusion principle. So we've done Pauli. So the Pauli exclusion. The Pauli's exclusion principle. What does it state or talk about? With the Pauli's exclusion principle, he indicated that the maximum number of electrons an orbital or each orbital can accommodate should be 2. And that 2 electrons, we should indicate their spins of opposite sides. The maximum number of electrons an orbital should accommodate is 2, and it should have the spin in opposite side. That is introducing the spin quantum number ideology over here. So the maximum, or let me simply indicate the max number of electrons an orbital can accommodate. An orbital can accommodate is 2, and should have opposite spins. So the maximum number of electrons an orbital can accommodate is 2, and it should have opposite spins. That is the Pauli's exclusion principle. That is the whole ideology. Is that okay? So now it means that taking the electron arrangements here, we can use any of them. So since hydrogen has only 1 electron, we've indicated that 1 electron here. But Pauli is also saying that we should indicate the spin of the electron. So since it's only 1 electron, we indicate only 1 spin. For helium, we should indicate its spin. Is that okay? In that order. Is that okay? So in the helium configuration, you have the 1s2. That is alright according to Pauli, but we should indicate the spin as well. The moment I decide to draw the spin in this form, moving in the same direction, it is violating Pauli's exclusion principle. Because Pauli's exclusion principle indicates that we should also show the spin of the electron, but it should be in opposite direction. Is that okay? It should be in opposite direction. So once it is in a parallel direction, the Pauli's exclusion principle is violated. So someone can choose to write it this way: you violated Pauli's exclusion, or someone can also choose to write it this way: you are violating Pauli's exclusion. For Pauli's exclusion principle, once the mass of electrons in the orbital is 2, you should also indicate its spin in the opposite direction. Is that okay? Let's take some example here for further clarification. Let's take carbon. So carbon is atomic number 6 with a configuration 1s2, 2s2, and then a 2p2. But we shouldn't forget that the p orbital exists in 3 forms. Is that okay? So we need to break it down. So we have the 1s2, the 2s2, but the p exists in the x, y, and then the z. So it simply means that we have the 2px, the 2py, and the 2pz. Is that okay? Please, are we good? Yes. So the carbon configuration, that is when you are breaking the p orbital down, it becomes like this. But let's hold on this, and then let me explain what I was talking about here. So once you're done writing the configuration, you indicate the spins in a box, but the spin should be in opposite direction like this. Since you have 2 electrons, you have to indicate the 2 electrons spin in opposite direction. So here we have the px, the 2py, and then the 2pz. But the electrons are arranged here, so we indicate the spin here as well. We will come to a detailed explanation on this one in the next principle. Is that okay? So this is the Pauli's exclusion principle. Once you indicate the max number of electrons to be 2 on the orbital, you should also indicate the spin, and always the spin should be opposite. Once the spin is parallel or pointing in the same direction, you are violating Pauli's exclusion principle. So in examination, they can just give you the configuration and then the spin configuration as well. And once the spin is indicated in a parallel form, they'll just ask you, looking at the configuration stated here, which principle is being violated? Which principle is being violated? So we are going to consider the spin arrangement over here, and since the spins are pointing in the same direction, you see that the Pauli's exclusion principle is violated. You can then say that the Pauli's exclusion principle is violated. Is that okay? Now the next principle.